All right. The next thing we're going to end up taking a look at is torque and the rotational version of Newton's second law. We'll first start off with how we end up computing torque. We mentioned what torque was in the last one. Remember that it's your lever arm crossed with the force that acts at that location of the end of the lever arm. So I gave an example in the lecture notes. Let's suppose we've got a pivot point. And remember what a pivot point means. It's the point about which something would rotate. So this would be the pivot point here. If I'm rotating my wrist like that, that's my pivot point here. Really, the line would be going through here if we're talking about that as being a pivot point. And your pivot line for a finger would be through the knuckle. All right. Then the lever arm is the distance from the pivot point to where the force is applied, and the force, and then crossed with a force. So remember, your cross product is the product of the magnitudes of the two vectors times the sine of the angle between them. So we compute what your torque is. In that particular case, we had a pivot point. We had a bar from the pivot point. You ended up having a force that's acting, like this on the diagram. So it's being pushed up in this type of a way. So let me get this. The way that it's, again, the thing about having this backwards on there makes life more complicated. Okay, let's see. So we've got the pivot point over there, and we've got our force acting, okay, like that. Okay, so, and notice the force is not acting at the end of you're acting at some point in between. It's where the force acts, not where the end of the object is, that you end up measuring your lever arm. And your torque there then we would compute as the product of the 2 meters distance times the 6 newtons of force on that tension times the sine of the angle. And remember, in terms of measuring your angle, you could either measure it as that 25 degrees or the supplement of that angle, which is, if you're looking at a different way of measuring your angle between it, you'd say 155 degrees, the sine of 25 and the sine of 155 is the same number, so it doesn't matter which of those you get. And the numerical answer you get is 5.07 Newton meters. Now, you might remember that a Newton times a meter is units for joules. And although that's true, a Newton meter in terms of torque is not measuring energy. And so we reserve the term joules whenever we're talking about something that's actually energy. So we do keep it as Newton meters instead of calling it, so it's not joules. In terms of your direction, to end up finding it, you'll end up using your right hand rule. So you end up pointing from your wrist to your fingers in the direction of your lever arm, which I believe will be going like this. And then you're crossing it with the direction of your tension, which will end up being out in that direction. So you curl it this way. And I'm using my left hand, but again, it's because the camera reverses everything. So we end up doing that, and then the direction of the torque is going to end up pointing out of your screen. To end up in understanding what that direction means, take your right hand's thumb and point it in the direction of the torque. Curl your fingers around while leaving your thumb out, just like the way we talked about angular velocity and angular momentum. So you should end up finding that in the screen, that direction would end up being counterclockwise. So you should do that. And like I said, unfortunately, trying to do this with the hands in a lecture class, that's easy to do, but with the camera reversing things, it causes problems. And the direction that you get there is the one that you'd expect. So if you're dragging it like that, you're going to expect it to end up accelerating around like that. So the direction should not be strange. It should make sense that if it's going to start spinning, it's going to spin the way that it actually does. The next thing we'll look at is using Newton's second law for rotation to find your angular acceleration. So, and to do this, we'll suppose we've got a meter stick that's suspended by a vertical cord that's attached to the 30 centimeter mark. So we've got, so the meter stick out like that, got a string up here holding it at 30 centimeters from the edge. Then I'll hang a weight over here at 60 centimeters hanging down. And that weight will end up being 75 grams, and we're going to assume the meter stick has a mass of 115 grams. What we want to do is to compute what that angular acceleration will end up being. Now notice if it's suspended from a location here, then the direction it's going to spin is going to end up being like this. So it will spin around the pivot point that's attached to up here. Again, if you play with something, if you hang something like this, you can see that's the way it will naturally pivot. So again, that's not something weird, that's not some weird physics thing, physics class thing. That's how things actually work. So we'll end up computing then what that is. So to find what my forces, what my torques are, I have to consider the forces that are acting on the rod. And there are three forces that are acting on the rod. I have a support force from the vertical thing holding it. I have the weight of the rod, and I have the tension from the cord, which is attached to the other weight. And in this situation, the tension in the cord attaching it vertically to the ceiling or whatever, it will not have a torque. And the reason for that is that force is acting at the location of my rotation. So my lever arm is 0. So if you have a scenario like that, you have no torque because your lever arm is 0 at that location. So there are really only 2 torques we have to deal with, even though there were 3 forces. So in order then to calculate the 2 things, we'll end up looking at the torque just due to the weight of the stick alone. So in order to end up finding that, we end up thinking about where is the weight of the stick. And remember we said the weight of an object occurs at its center of mass. So the center of mass of a meter stick is obviously at the 50 centimeter line. It's the midpoint of the meter stick. So to find your torque, you end up finding the distance then from where the object is attached. Excuse me, over here. Everything's backwards on it. So where it's attached up here, attached up there, then the 50 centimeter line over here, this is where the weight is. So this is 30 centimeters here, 50 centimeters from the end to the center. So the difference here, that's your 50 centimeters minus the 30 in your notes. So that's where that 0.20 centimeters, 0.20 meters comes from. So you multiply that distance, the lever arm, by the weight, which of course is the mass times little g, times the sine of the angle. And in this situation, we're asking to find what the torque is whenever it's horizontal, because eventually it will tilt, right? So it won't stay that way, but at the moment when it's horizontal, then that's 90 degrees because it's going straight down and the lever arm is straight across. So you compute so the angle is 90 degrees, so the sine of 90 degrees is 1, so you don't have to worry about it, and that gives you then 0.22 Newton meters as the torque from the stick. We also then calculate the torque hanging 75 gram mass, and again we always assume that the mass of a string is negligible. So we end up finding then, since it's attached at 60 centimeters, the pivot point's at 30, then that distance from the pivot point is 30 centimeters. So that's the 30 centimeters times the force of the torque, which is equal to the weight of the hanging weight, then times the sine of 90 degrees, which is the angle between your lever arm out and the weight going down. So that gives me 0.206 Newton meters. And so we next look at which directions the torques are, because the torques can be in the same direction or opposite. So for the meter stick, your lever arm is to the right based on the picture. The force is down. So if you end up doing that with your right hand, you should end up finding that your torque is going into the screen. Similarly, the two directions are the same. The lever arm is also to the right for the weight, and the force is still down due to the tension. So the torque there is also going into the screen. So the total torque, we add them up. So the total torque then is the sum of the 0.22 and the 0.206, which gives me 0.426 Newton meters. And we will, then to find the moment of inertia, we end up considering the meter stick. The meter stick is, we can think of it as being two parts. I have one part to the left of my pivot point, one part to the right of the pivot point, because I have formulas for something that rotates around an edge. So this isn't attached to an edge, it's attached in the middle. So there's not a sort of in the middle. There's one exactly middle, but there's not one sort of middle. So to end up finding my moment of inertia there, I end up taking 1/3 the mass times the square of the length for each of those two pieces. The 1/3 ml squared, of course, comes from the table. So we calculate then the moment of inertia for the short side. So the mass is 0.30 over 100 of the total, because there's only 30% of it that's on that side. So you get the weight of just that piece, which is 0.0345 kilograms, as I computed, and then that distance squared. So you find your moment of inertia for that one, which is 0.00104 kilogram meter squared. Then we do the same thing for the right side. So they are now 70% of the weight is on that side. We multiply the mass of the stick, so that gives me 0.0805 kilograms. So then my moment of inertia there will be 1/3 ml squared again, and that will be 1.323110 to the negative second. So I add my moments of inertia, because moments of inertia add just like masses add. So I get 1.4110 to the negative second kilogram meter squared. So finally, at this point, now I know my torques, I know my moment of inertia, so now I have enough to find my angular acceleration. So my total torque is 0.426 Newton meters. My moment of inertia is 1.4110 to the negative second kilogram meter squared. So I solve for my angular acceleration, and that gives me 30.2 rads per second squared.